It's interesting. I was just reading a document from 1993 on the International Space Station on the effects of vacuum on different materials, and they were concerned with the amount of cold welding that was going on. And the testing was done at the Sandusky vacuum chamber, the Glenn Research Center, and the article is in 1993 from Joyce Deaver. And what was interesting, they were looking at stopping metals from welding themselves together in the different coatings they were using, but it also claimed that Teflon and other plastics were being completely dried out at a torr level of 10 to the minus 6, becoming quite brittle and cracking.
How did they do that? Did they take it right down to 10 to the minus 6, like right down to it, or was it 10 to the negative 5 point da-da-da-da-da?
As close as they can get in the chamber, and that is the maximum that that chamber can produce. And the other problem they were having was flaking of materials during that time. So basically any plastics, polypropylene, polyethylene-based plastics are pretty much useless if you go past that level of vacuum. And of course the moon is quite a bit substantially farther than that. So on the basis of the film that the Apollo missions claim to have had, especially the Hasselblad film, the way film is produced, the way it's manufactured, are just very thin layers of plastic, polyethylene type plastics, and within that plastic is an emulsion layer which is very reactive and captures the image on the film when the shutter is open. That particular emulsion is gelatin based, and that gelatin base is made from animal gelatin. It has never been able to be successfully synthesized. That emulsion layer is laid down. Between those layers, it can be a single layer if it's a black and white photograph, or it can be multiple layers, and each of the layers can be colored. And I believe you have an image of that to show the different layers on it. The difference between the standard type film base, which would crack, rip, or tear as it's being pulled through the camera with the gears, was enhanced by using ester-based film. And an ester-based film used by Apollo that they claim were able to withstand the vacuum and the radiation of space. Of course, the ester base itself is nothing more than a polyester layer on the backside to make the film tougher. And it does make it tougher. It does make it very strong so that it won't tear, rip, or crack when it's being pulled through the camera. That emulsion still has to remain exposed on the other side through the very thin layers. And as it's wound through, it winds up right up against the reso plate on the camera so that when the shutter opens, it can take that image. Hasselblad, because that emulsion is so reactive, built a very precise camera to control the reaction and how that emulsion captures the film. And it's a very precise instrument that they've produced, not only from the camera lens, and the camera lens, when you're adjusting the aperture, opens up to give a even lighting right across the entire reso plate, so it doesn't fade off in the corners or to the edges or anything else. It's a very even mapping of the light coming in. That is one of the design features that a Hasselblad camera has. The other portion of it is the precision of the shutter speeds on which that camera opens and shuts at. The emulsion is very susceptible to environmental conditions such as barometric pressure, humidity, and temperature. And the camera is designed to control those environmental factors, as well as the ambient light coming in, which everybody knows how a light meter works. That's why a Hasselblad camera is such an expensive and precision instrument, and if you operate it correctly, you can have a superior image. coming off of there. But the gelatin itself is so reactive and so susceptible to environmental conditions, taking it into space, putting it into a vacuum, having the actual plastic layers being pulled apart by the vacuum, or if there's a small perforation in the film itself, is simply going to off-gas. All of that material will be damaged. The emulsion will be damaged. There's absolutely no way to harden film itself for radiation or the vacuum itself or the temperature ranges. And because it's an animal-based emulsion, it falls into the same freezing and boiling temperatures as basically the same as water is. It'll freeze right down solid. The emulsion will not work if you go beyond those temperature ranges. Being in space and being on the moon, those ranges are much greater than what the camera and or the film is capable of handling. If you take the fact that light itself is part of the radiation spectrum, and that is what is making the reaction, that's what's capturing the image in 1/250th of a second or 1/500th of a second or 1/25th of a second on your settings. That's how fast that emulsion is going to react. When you get into the radiation of space, and even if you take NASA's very mild radiation numbers, and we'll look just at the astronauts themselves, we won't look at the general radiation that people question, but we'll just look at NASA's claimed absorption rate that the astronauts had during the entire trip they were out there. And basically, to keep it in simpler terms, we'll just deal with it in number of x-rays.
If you compare it to the number of dental x-rays,
yeah,
people can understand it a little better.
Yeah. At the very lowest settings I've seen from documentation, some of the lowest numbers of radiation of the absorption rate were equivalent to about 3 x-rays a day, which is ridiculously small. So on an 8-day trip, they absorbed about 24 x-rays during the trip. Of course, everything else within the craft is going to be absorbing the same amount of radiation, included the film. Now, even at a small percentage of an x-ray, the film would become fogged, completely fogged. You'd be able to see it visibly on the film at one full x-ray.
When you take a look at flight crews that have to wear those radiation badges, all of them do, because they fly at 32,000 feet or above. And if they go up any higher than that, like when they start getting into 60,000 feet and up, now those badges are going to start to fall.
That's right. Well, as a matter of fact, they changed. I know stewardesses that couldn't fly over the poles because they had absorbed too much radiation, so they put them down because the Van Allen belts are less dense there, and there's more radiation coming in at that level.
Mentor Pilot had a really good one on that. He had a good video on showing that, demonstrating that. So if you're going to be traveling any higher than 32,000 feet, you're going to start having fogging on that film. Even at a low rate, you're still going to have something showing on that film that's visible.
That's right. As a matter of fact, it doesn't just affect the film, it actually affects electronics on a plane as well. And even if the absorption rate is claimed to be only 3 x-rays a day, at one full x-ray, the film is fully exposed and fully finished. And that is no different than putting it through an airport scanner and destroying the film. Like, everybody knows that film could not go through those machines.
I mean, in the 70s, coming back from Europe, they had to
right.
take the film, hand it to the customs official, and then they would look at it, pass it back to you. And that's the way it worked.
That's right. So even at the lowest numbers you can find on radiation, at the equivalent of 3 x-rays a day, the film would have experienced 24 full x-rays in 8 days and been destroyed many times over. And then it is the location where the film is stored. Some of the film was stored in the descent stage of the lander, so it's exposed to not only the vacuum but the radiation outside during the entire trip. The back camera on the outside of the CSM, the film was loaded there from launch. It would have experienced all of the temperature ranges as it travels through the launch cycle, right through the Van Allen belts with the highest form of radiation, and apparently it worked just fine, taking 1 frame per second as it orbited the moon. They're 6 days into the trip when they picked it up and did the spacewalk to physically pick that film up. And there is no damage or fogging or anything on that film, and there's absolutely no way that the plastic layers would survive the vacuum, and there's no way that the film would survive the radiation.
When we tried it with the vacuum chambers, what ended up happening was when you put the film in there, you did a comparison, and then you did one in the chamber. And when you take them out and you look at them, and you're going, holy smokes, hang on a second here. This one here, the experimental film, the black and white one, right, we did one complete cycle of vacuum. And it didn't show a heck of a lot. But now you go 1 cycle, 2 cycles, 3 cycles of vacuum. Now guess what you have? Now the fogging starts and the black and white film strip. Now when you go to color and you do the same thing, you start to see the hues. The tints start to change. On the experimental film, and you start going to darker places, and you'll see that up on the film, right? We're going to show you that. And what will happen is that now the hues start going, and the color starts washing, and the tints start going crazy. And that was with 3 cycles of vacuum, and the film, experimental film on the color being brought up to 130 degrees centigrade through a UV light shining through the lid of the vacuum chamber. And the other one we did was with the smaller chamber with the film in that inside of the vacuum chamber sealed off so that the heat cannot be transferred into the second vacuum chamber itself. You have the same thing happening. Again, the tints are washed out. And even if you take the color film and you do just one cycle of vacuum and you compare the two, you still see the tints are starting to go. Now, when you do 3 cycles of vacuum and you add that heat lamp on to the top of it, the light shining through the lid, 2 feet up above the chamber, now the hues all go to pot. Only when you're letting less light through the aperture. And that's our problem.
Well, the thing is the film itself would have cycled many times as they pressurized and depressurized the lamp. Wider temperature ranges when they're out on the rover, fully exposed. So they're out in the light, then they put them underneath the seat where they're going to cool down, then they pull them back out into the light. Those cycles affecting the film, everything in the environment affects that film, and that emulsion layer in between is so reactive to the environment so rapidly. If you can capture an image in 1/250th of a second, it takes very little to damage that, to ruin the image if it's not being controlled. And there's no way that they could control the temperature ranges. There's no way they could control the pressure ranges or lack of pressure ranges the film was being affected to.
And the film is very fussy stuff. You can't fool with it. Even when you're developing, the temperatures have to be exact. You have to keep the temperature constantly in the Patterson container. It has to be at 101 degrees Fahrenheit, and it has to stay that way. So you have to make sure that you have a container of water that's constantly heated up where you can keep moving and taking out, moving and taking out to make sure that 101 degrees is there, and not 102. So these guys are saying that they're out there with these space probes, lunar probes back in the 60s, and they're saying film. Well, let's see here. They're taking film and they're developing in space. Well, emulsion was exactly the same. And the difference with that emulsion is that some of them have triangles, some of them are squares, rectangles, combinations, and that's how they get the nicest contrast, the greatest contrast.
The scanners themselves they claim to use on those LROs to capture the image and digitize it would have to be 10 times faster than what they're using today to do the deep fake images, because the fastest machines today are capable of doing a deep fake at 1 frame per second, and they claim they were doing it at 10 frames per second. Just absolutely incredible. Their little computer was so much faster than the ones we have.
How are they gonna take the film and then snap the pictures? Oh, by the way, the film was developed in space too on the earlier LROs, right?
Exactly.
So the webbing. So now they're claiming that a layer of webbing went between, and that's what had the developing on it, the developing solution on it, right? And after it went through its process, then it goes and peels off. Oh, you'll see that in the diagram that we're going to show you. And then you have the little Vidicon camera there taking the pictures, and then it's scanned. Well, guess what? We didn't have scanners until when? 80s? Something like that?
The other problem is with a solution in space and running the film through it, you're in a weightless condition.
Yeah, and here's the temperature control, right? You have black and white film. In the black and white film, this ESTAR film has to be kept at 80 degrees Fahrenheit when it's being developed. In the LRO probes, they're saying that, well, we maintain the temperature, we maintain pressure, it depends what article you read, 1 psi, 2 psi of nitrogen gas. And that's what they're using for the atmosphere. And the atmosphere would have to be heated at least to that temperature, or else the film will not develop. All you're going to do is get a blacked out frame. Tim Trumbull has said that many times. And Tim is our expert, resident film expert, who has worked on a great many films in the Hollywood industry and in Australia. He's done it all. You name it, he's done it. So there's no one that can turn around and say, you don't have any experts on your team, and you don't have this and you don't have that, like the Birdie Bunch. Right? They make all sorts of claims, right? And they're just full of crap. They don't look at articles. They don't know that film emulsion is made from pig gelatin, and that's usually where it comes from. It comes from pigs.
They don't know that it can't be synthesized, can't be modified, it cannot be hardened for the environment of space. It must maintain, it has to be fully reactive at all times to capture that image, and it is affected by every environmental controls here on Earth, and that's exactly why a camera is such a precision instrument to control that. The very fine settings to adjust for barometric pressure, for humidity, for air temperature, and for ambient light. That's what a camera is about. It's controlling what is being captured on that film.
But here what happens is when you get guys like the Birdie Bunch, or you get Phil Plait, or One Big Monkey, it doesn't matter, they're all the same. They're all in the same group. Somehow they feel that it's magical film, when it's not magical film. Anybody can go out and buy it. I mean, you want to pay $2,200 for a little roll of it. That's another story, right? Like we did. We bought the hand-wound black and white film, which we got from California, 10 rolls of it. And in matter of fact, we even ruined one vacuum chamber.
That's right. A vacuum chamber that should be 3 times stronger than it's rated for is affected by a small increment of vacuum from a slightly larger machine.
No, but it's all this, right? Well, it's ESTAR based and it's PET based and it's this and it's that. When you go and you look up in NASA's journals or you look up on their files and their PDFs that you're going to show you here, yes, it's ESTAR film. Yes, it's 160 ASA. Yes, it's this. Yes, it's that. The PET is only a carrier for it. And if that emulsion dries out, it's game over.
That's right. The polyester layering that makes that an ester film is just on the back side of the film. It can only be on one side. If you put it on the other side, it wouldn't capture anything. You have to have those other polypropylene layers of plastic on there that sit right up against the reso plate, fully exposed to everything. Or when the camera exposes it with the shutter, when it opens and captures that film, it's so reactive.
We took 2 experimental rolls of film that were just there for, let's say, bonus material. What happened when a tiny little bit of light got into that Patterson jar by accident?
It was gone in a second.
Instantly gone.
Yes.
Written off. Everything black.
Everything reacts that quickly.
And when we played with the temperature of the film, what happened? Pull it out, everything's black. So how NASA did it with these probes, with the LRO probe in the 60s, using a webbing material that had all the developer and everything on it, and then to go through rollers, come out, and it's developed. It's sitting in a 1 to 2 psi nitrogen-filled chamber, but what are they using for temperature control? Film is a finicky thing.
You're in a container. How are you going to dry it? You're going to have to purge that continuously to be able to dry the film.
What are you going to use? You're going to send a guy up with a pair of squeegee tongs?
From just the processing of the chemicals itself, how are you going to clean those chemicals off when they're being processed? They're in that atmosphere. They're completely encased in a container. All those chemicals that are vaporizing off in there are going to be in the air. Contaminate the film. Every piece of equipment in there will be contaminated with it.
I mean, what they basically have up there is a Kodak photo lab. And they claim that's going to work in space. In zero gravity, by the way.
Everything's going to be floating around. You're not going to stop it from going everywhere. No. Liquid's in a vacuum, in weightless condition, and you're going to sit there and say, oh, well, we'll just run it through this tray of stuff.
There they have scanners, digital scanners in these probes. 1965, 7? Come on.
Did not even have a hard drive to store the data on if you could capture it. And all those liquid chemicals sticking to every piece of equipment in there because it's in a vacuum. Yeah. It's in weightless conditions, sticking everywhere.
Dear God.